right? So we're getting awfully close. So I'm going to talk to you about, again, something completely different. Vaccines saved clearly 6 million lives in the world last year alone. 700,000 kids in the US are alive today because of vaccines. But there's one big problem with vaccines, and that is most of the really effective ones you have to keep in a fridge. You can't freeze them, you can't heat them up too much. And this is clearly a problem when the rain falls in Portland and trees fall on the power lines, but much, much more importantly in the developing world, which, as we all well know, has a lot of places that could really use some good and, in fact, some of the newer vaccines that are coming along. What happens in the developing world? Well, you get transportation like this, on the back of a donkey. And I was recently quoted in a certain journal like New York Times saying you can't put a fridge on the back of a donkey. Really long power cord, but that's about it. So we said, who can ask? Well, ask T-Rex. T-Rex always has the right answer to questions, right? Well, this is actually, of course, not T-Rex. This is a fossil T-Rex at the Field Museum in Chicago. And that brings me to the research that's being done in my lab at Portland State University by this graduate student, Dr. Jim Laidler. Yes, already a doctor before he made a graduate student in my lab. He says it's his midlife crisis, working on virus fossils for his PhD in my lab. Particularly, he's been working with one virus in particular, which is bacteriophage T4. Why bacteriophage T4? Because it's beautiful. But also, it's got this really distinctive shape, and we can get lots and lots and lots of it. So basically, for about the first half of his PhD thesis, Jim showed that you can take bacteriophage T4, coat it in silica, and see that it really does get a very clear silica coating. On the other hand, uncoated, as you can see at the bottom of the slide, looks very, very different. Unfortunately, what Jim also found is that the longer you left these viruses in these conditions, they basically became blobs. And blobs are not something you can put in a museum floor. You're not going to use it for detecting virus fossils. But Jim said, well, what actually happens then to the viruses once they get coated in silica? And we know places where they do get coated in silica. It turns out that they lose huge amounts of infectivity. The blue line here is bacteriophage T4, again, our favorite virus, at least for his project. 4 orders of magnitude loss of infectivity in coating with silica. Vaccinia virus at the bottom in the red line, more than 4 orders of magnitude loss of infectivity. Hot spring virus that you actually find in some of these silica depositing environments, medium loss, and then a few viruses don't seem to care whatsoever. So that was really kind of interesting, but not terribly surprising. The really cool thing is that Jim discovered you can actually reverse this silicification. You can take the silica coating off of these viruses. And lo and behold, once you have done that, these viruses come back to life. So this, and it's his terminology, these are the zombie viruses. If you look at the blue line, you see it comes almost all the way back up to where you started. And remember, this is a log scale. Same thing with Vaccinia virus. Even those viruses that are less inactivated still regain a lot of their infectivity once you take the silica coating off. So that, okay, was really cool in and of itself. But the other thing that Jim noticed was that now if he takes these viruses that have been coated in silica, it turns out they are now hyper-resistant to insults. And the particular insult that we used was drying. A, because it's easy to do, and B, it turns out bacteriophage T4 is incredibly sensitive to drying. You put it in a speed vac, zero infectivity whatsoever. However, you coat it in silica, it's stable for over 2 months, losing basically no infectivity. So is this the solution to freezing or things getting too hot? We think that it might be, and again, that's a pretty big maybe. We're in the process right now of doing more experiments, particularly looking at things like flu, yellow fever, that other one up there. There are no vaccines yet, but a lot of the vaccines in development are clearly highland stable. We need partnerships to do this, so please come and find me afterwards. I really want to talk to you about this stuff. And this way, we're hoping we're going to be able to put those vaccines on the back of the donkey, being able to get them out to the developing world, save those 1.5 million kids that could be saved every year with vaccine-treatable diseases that can't get them. So that is how T-Rex is hopefully solving the vaccine cold chain problem. So that's our connection. If you want to find me, there are a couple of different ways. One, grab me right afterwards, or go to Yellowstone National Park, which is where I do most of my research, poking around hot springs. You can also just Google virus hunter at Portland State University, because that's kind of how I'm known. And with that, thank you.